Cliff Meidel expressing his gratitude to the men who brought him back to life. In 1986, while on a construction site, he accidentally jackhammered into 30,000 volts of electricity, 15 times the amount in the electric chair.
Most of the wounds were to my leg area, where I had a third of the knee joint burned away on both legs.
He had 2 massive gaping holes in both legs. You know, surviving, I'm surprised. Not losing his legs, I'm stunned.
The paramedics got back in the hospital and said that they actually revived him. Not only was I shocked, but I was almost wondering, what kind of life is he going to live?
It was a very difficult time for myself and my family. I was going to have my legs amputated, and it was the persistence of my mother and father to go out there and seek out a physician that would be able to save my legs. It was kind of a bleak time for myself and my family.
After 3 years, more than 15 surgeries, and against all odds, Meidel was walking without crutches.
At first, it was my dream to be able to run again, so that was kind of the driving factor for me to go into the gym, go to rehab, and keep pushing and pushing. And then I finally found out that, I wasn't going to be able to run again, so I kind of thought, well, if I do sports that involve the upper body, I can maximize myself that way. That's why I got into kayak paddling.
Paddling became an integral part of Cliff's rehabilitation, helping to strengthen him physically and heal him emotionally.
I love challenges. The more effort that you put into the sport, the better the outcome is going to be.
Cliff's determination and passion led to an outcome that is the ultimate for any athlete, a spot on the U.S. Olympic team. He competed in the Atlanta Games in 1996 and again in Sydney in 2000. Can you tell me why you love kayaking?
Yeah, I really enjoy kayak paddling because it allows me to get out there in the nature like we are right now.
Is it true the first time you got in one of these, you had to be carried to the boat?
Yeah, actually, when I started canoe paddling, before I got into the kayaking, the coach had to lift me into the boat because I still had crutches, and so...
Did you have any fear?
Yeah, I was afraid because I had these big knee braces on, and I was afraid that I wasn't going to be able to swim. I would just sink.
Right, you could drown. After everything you've been through, now you're going to get in a boat,
yeah.
You can't use your legs?
I think that competitiveness and wanting to do it and be a part of the team kind of overcame those simple, basic fears of being able to swim. You guys got me out of the cardiac arrest and helped me progress in life.
These days, Cliff gives inspirational talks to firefighters, and especially to other burn victims, urging them to never give up. You think that's why you were saved?
I don't know. My mother believes that. If I can help others, then I know I've done my job.
And he's just been named spokesman for the Construction Safety Council, hoping to lower the rates of electrocution in this country.
So 30,000 volts of electricity. Survived, had a heart attack. And obviously his knees are not working properly. I think the bones almost melted, but that was the extent of it. So the question is, what made it survivable? Let's run the numbers on this guy just to get an idea, because there are a couple of things that we need to discuss. 30,000 volts. I'm going to go with the Mythbusters magic number of 10,000 ohms, the uniform resistance for the entire body. So what's the amount of current going up his legs through his body, if that's the case? All right, so we know that the current is going to be proportional to voltage. It's going to be inversely proportional to resistance. That's the Ohm's law. So 30,000 divided by 10,000 is going to give you 3 amps of current. Guys, 1 amp is enough to kill someone. If you go with Mythbusters numbers, all right, this guy should have been dead, yet this guy was able to survive. So the question is why? When you have a question like that, how do you answer it on the test? It's kind of weird because you guys come up with some interesting answers, which usually tells me that there's knowledge but not enough understanding. 3 amps of current. If the current gets to the heart, it's going to be 3 amps. And then if this current, the duration of this current is as long as the duration that this guy experienced, he would have been dead. He would have been dead. All right, so the duration matters. The amount of current matters, also the duration matters. So immediately you know that it's not going to be 3 amps of current getting to the heart because of the simple reason that the guy survived. More realistic number is about 100,000 ohms. All right, so this is the number that I end up getting from Wikipedia. We're going to have the same number in most of the physics books. It's the same thing. And if this was in person, we would actually be measuring this in class. This is fairly easy to measure. All right, so this would be the skin's resistance. The skin is highly resistant to current, so you end up getting 0.3 of an amp of current. All right, would that be large enough to kill? This is large enough to give you a heart attack. And that's precisely what was happening to this guy. He was having a heart attack. And eventually they were able to rescue him. All right, so somebody's having a heart attack. So what do? We pump in about 20 amps of current into the chest cavity while hoping that at least an amp of current is going to get to the heart. And then you shock the heart for a fraction of a second, for a thousandth of a second, a fraction of a second, long enough to reset it. All right, so you briefly stop the heart. It resets itself. It's an electrical organ. All right, so the question is, how do we control the discharge time? All right, so that was always a question. So you have obviously you have a defibrillator. In essence, that's a capacitor. You just charge it up, and then it deposits about 20 amps of current within 0.02 of a second. So this duration is important. You don't want to make it a second long or 2 seconds long. If you could do it that long, obviously the person's not going to be able to survive. That acts like an electric chair. And once again, when it comes to flash photography, the timing is important. You're supposed to be able to capture the bullet as it's going right through the banana. So notice that discharge is about 0.3 of a millionth of a second. That's what you're looking at. So how do you control the timing so precisely? How does the magic happen? In essence, you're dealing with controlled lightning. How do you control the duration? All right, so resistors in series as well as in parallel. So we discussed these concepts before. So this time around, we will get to do things a little bit more formally and mathematically. All right, so we got appliances. In this case, we got 3 light bulbs, which are going to be connected to each other in essence, in series. All right, so what do you expect is going to happen? We discussed that before. It's like a traffic flow, right? All right, so something happens while you're driving, someone texting, it's going to slow down the traffic. And if there's an accident, it's going to slow it down. If there are lights, it's going to slow it down. So every time there's something that resists the motion of the traffic itself is going to slow down. The same thing is going to happen to the charges. All right, so every time the charges are moving in the same direction, and then when they encounter resistance, they will slow down, and they will slow down. The resistance is going to go up, the current is going to go down. The current represents how fast the charges are moving, in this case. All right, so let's come up with a simple derivation for this one so that we have an idea of how to compute for resistance. Commonsensically, you know what to do, right? Just add up the resistances. Now, following the rules of algebra, let's check to see if we come up with the same thing. All right, so the voltage is what drives current, and resistance is what's going to diminish it. So what we're looking at is the Ohm's law, in essence. All right, so this is the amount of voltage which is going to be supplied by the battery. This is the amount of current traveling in this direction. And this is the amount of current which is going to be going through each and every single resistor, in essence. So what is the total resistance of the circuit? All right, so the current is going to go through this resistor, it's going to go through that one, it's going to go through the last one as well. So logically speaking, we know that it's just going to, resistance values, which is going to add up. And then what's going to happen is the amount of voltage supplied by the battery is going to be the same as the voltage drop across the first resistor, plus the second resistor, plus the third resistor. So the voltage supplied and the voltage drop, total voltage drop across the circuit will be the same. What that means is the amount of energy supplied by the battery is going to be exactly the same as the amount of energy used up by each and every single appliance, otherwise known as the conservation of energy principle. All right, so the amount of voltage supplied is going to be the same as the voltage drop across the first resistor, appliance, plus the second resistor, the appliance, plus the third resistor or appliance. They mean the same thing. All right, so the amount of voltage supplied and the amount of voltage gain as well as the amount of voltage used up will be the same. All right, so that used up voltage is otherwise known as the voltage drop. So the voltage drop, total voltage drop is going to be the same as the total voltage gain, or the amount of voltage supplied by the battery. All right, so the voltage across the first resistor is going to be voltage drop across the first resistor, this term, second resistor, this term, and the third one is going to be that term. And notice that it's the same current, which is going to be going through each and every single resistor. So the current 1, 2, and the 3 will be the same. So I will just call them I. Now what I'm going to do is I'm going to factor them out of the equation. All right, so this is the voltage supplied by the battery, which is this. This is the same current going through the entire circuit. And this is the total resistance. Total resistance is the summation of our resistance values. All right, so the total resistance is the summation of our resistance values. All right, so we knew that commonsensically, mathematically, also it works out that way. All right, so the overall resistance is going to go. Use the best. Simple problem that we're not going to get to do because it's too simple. It's a demonstration problem. You're looking for the total resistance. What do you do? This plus that. Boom. You end up getting that. Okay, so I think I have the solution for this one. Just make sure that you know. Obviously, you guys know how to add up numbers. That's not the point. Given that, you know how to figure out the current and the power dissipated within a resistor, and the total power delivered to the resistance by the battery. All right, so you got my solutions. Make sure that you go over these problems. Okay, these are simple enough, not worth my time. I'm not going to be wasting my lecture time on something, but know how to do it. All right, the basic stuff you need to know, and you need to be able to take that stuff with you into your engineering classes. All right, so what if things are connected in parallel? These resistors are connected in parallel. Then what do we do? All right, so what's going to happen is we discussed that before, conceptually. Every time you provide a current and alternating path, the resistance is going to go down. All right, so the overall resistance of the circuit is going to go down, which means that the amount of current in the circuit is going to go up. And we discussed that using a traffic analogy. All right, and then I said, this time I said, if you're looking for the total resistance, I said you have to add up the individual resistance values reciprocally, and it's going to give you the reciprocal of the total resistance. All right, so the way we add things up is kind of weird. So the question is, how do we come up with that formula? Obviously, we're not getting stuff from space aliens. All right, so there's got to be a reason for it. All right, so one of the things that I want you guys to notice is this time remaining constant is this time what's happening is the current's coming in. This is the amount of current which is supplied by the battery, and then it hits the junction right at this point, and then it splits. Some of the current is going to go this way, some of the current is going to go that way. Then it's going to hit a junction again. The current is going to split again. Some is going to go this way, and some is going to go that way. All right, so the amount of current supplied by the battery, this is the meaning of it, is going to be the same amount of current in each and every single branch. I didn't say that. All right, so the amount of current supplied by the battery is going to split into the number of branches that we have. All right, so amount of current supplied and the amount of current going through each and every single resistor is going to be the same. This is otherwise known as the conservation of charge principle, something that we discussed the first week. All right, so let's take a look at the derivation of it. So the current is going to hit a junction here, and it's going to split. Part of it is going to go that way, part of it is going to go this way. And notice that we got 3 branches, so the current is going to split 3 ways. Okay, so how much current is going to go through the first resistor depends on the resistance value. How larger the resistance is, the smaller the amount of current is going to be. So you kind of expect that. As smaller the resistance is, the larger the amount of current is going to be going through it. Okay, all 3 branches will have something in common when resistors are connected in parallel. What they have in common is the voltage drop across each and every single resistor is going to be the same as the amount of voltage supplied by the battery. All right, so that's the amount of energy supplied by the battery is going to be the same as the amount of energy used up or converted to heat or light across each and every single resistor. All right, so that's what they will have in common. All right, so mathematically, if you're doing a derivation like that, once again, we start off with the Ohm's law. This is the voltage which is going to be supplied by the battery. This is the current which is coming out of the battery. This represents the total resistance of the circuit. So what we're going to do is we're going to try to come up with an expression for the total resistance of the circuit when the resistors are connected in parallel. When the resistors are connected in parallel. All right, so that's what we're going to try to figure out. All right, so one thing that we know, this current is going to split into the number of branches that we have. And in this case, we got 3 branches. So the current is going to split 3 ways. And we can compute the current in each and every single branch by using the Ohm's law. So the only thing we have to do is take the Ohm's law from here. I'm hoping that I'm going to get to it. And then solve for I. Oh, I've done that. All right, so this is the current through the first branch, current through the second branch, current through the third branch. Okay, so we got the current values for each and every one of them. And then I also mentioned that the voltage drop across the first one, second one, and the third one. When I say one, I mean the resistors will be the same, right? All right, so which means that I can factor out the voltage drop across each and every one of them is going to be the same as the battery. And then this is the Ohm's law. All right, so this is the amount of current coming out of the battery. This is the amount of voltage supplied by the battery. And the expression that you're looking at is going to be the reciprocal of the total resistance. All right, so this is the reciprocal of the total resistance is going to look like that. So if you're looking for the total resistance of the circuit, you have to add individual resistance values reciprocally in order to get the reciprocal of the total resistance. That's the way I say it, because that's the way it is. All right, so that's it. Straightforward. Once again, there's example problem. All right, so when the resistors are connected in parallel, we didn't do it numerically. Obviously, you will have to, there's going to be a conceptual test question on it. When they're added reciprocally, the total resistance is going to be smaller than the smallest resistance that you have, resistance that you will have in the circuit. So when the circuit is wired parallel, the overall resistance is going to go down. B is the best answer. In fact, the overall resistance is going to be smaller than the smallest resistance. So what happens? The resistance goes down and the current goes up. All right, so once again, a simple problem. We're not going to do it in class. It's just not worth my time. I think I'm just look at my solutions. Just go over it. All right, so know how to compute the total resistance of simple circuits with resistors set in parallel, and then be able to do the current, the power dissipated, power supplied. Okay. All right, so how would you add up the resistances if you're looking for a total resistance? So you just add them up reciprocally, right? And that's all you have to do. So when you add them up reciprocally, it's going to give you the reciprocal of the total resistance, and then you invert it, and then this is the value coming out. All right, so that's the straightforward part. Okay, now this is a little bit more involved, not complicated, it's slightly more involved. Okay, so what if you have a circuit that has a combination of resistors in series as well as in parallel? How would you handle something like that? All right, so study this, take all the time you need. Think about what it is that you would do. I'll give you 10 more seconds to handle something like this. These are not complicated problems. The way you would do this sort of stuff is procedure. It doesn't require a lot of thinking. You just do the obvious stuff, all right? Notice that these two are in series. So what do you do? Add them up. Okay, so this resistor plus that resistor value is going to give you total resistance here. And whatever the total resistance here now is parallel to this resistor. Now you have to add them up reciprocally. Now the combination of 3 is going to be located here, so it's going to be in series with this one. And then now what do? You just sum them up again. Just ignore the numbers, just follow the process. This sort of stuff is procedural. It doesn't require a lot of complicated thinking. All right, so add up these 2 resistance values first. And then obviously you do add them up linearly, so it's not a big deal. This plus 5 is going to give you that number because these 2 are in series. Now these 2 are in parallel, so what do? We add them up reciprocally. And then when you add them up reciprocally, you end up getting a reciprocal total, which means that you have to invert that. And as soon as you invert that, now you're left with this number. And now these 2, it's the same current, which is going to be going through both of them. So which means that they're in series. So now what do? You sum them up again, and then you end up coming up with one single amount. All right, so it's not that complicated. If I were to give you a multiple choice test on this one, I'm going to start giving you guys some multiple choice test math tests as well, but I'm going to make that extra credit. I think I'm going to start doing it this week so that you have more practice, because I want you guys to be able to use a variety of formulas and do maybe like 1 or 2 step computations, something like that. All right, the short work problems tend to be, I want to see the details. Those problems require thinking and conceptual understanding. And the multiple choice questions usually require that, hey, I recognize the formula, I have a simple enough problem, I know how to solve it. So that's what I'm going to go for, but I'm going to give you extra credit for it. This would be a nice multiple choice test question. A couple of computations and you're done within less than a minute usually. All right, so far so good, guys. This is at the level of high school physics. All right, so let's take it up to the college physics, college level at this point. So the household circuitry for the reasons that we discussed is connected in parallel, obviously, so you can have all the household appliances running at the same time, while you can turn it on and off some of the appliances without shutting down. All right, so the household appliances will be connected in parallel. All right, so the best answer is the second time you guys are seeing this question, so let's move forward. Now let's talk about the purpose of this lecture. The purpose of this lecture is this: what if you have complicated circuits? All right, so we're not in high school. Let's just do some university level physics at this point. All right, so a circuit that looks like this. All right, so it's a simple enough circuit, but it's a weird enough circuit because you're thinking, wait a minute, I can do this. It's not a big deal. It's not that complicated. But I got news for you. I got 2 batteries within the circuit, and this kind of represents the car. All right, so you got the headlights here. This is the car's battery. You got the alternator here. My question is, how much current is going through the headlights? How much current is coming out of the battery? And how much current is coming from the alternator? Okay, this is a simple enough circuit, but how do you solve a problem like this? All right, you could try the methods. Oh, these are I don't know, resistors in parallel maybe, or it's a combination of resistors. You can come up with those kind of ideas and try to solve this problem. Only realize that this is not an easy problem to solve. It looks easy, but it's not. The reason is because you got 3 unknowns. You got 2 batteries, you got 3 unknowns. I'm interested in the current going through the headlights, current coming out of the battery, which is the one in the middle. I'm also interested in the current generated by the alternator. All right, so this is the electrical system of a car. So how do we figure that out? The only thing you know is you got a 12-volt battery, and then the alternator is going to be able to generate 14 volts of power. All right, so how do we do a problem like that? Okay, let me give you this solution before we do initial work. You got 3 unknowns. What do you need? At least 3 equations to solve for 3 unknowns. So the question is, how do we generate those 3 equations? Well, enter this guy. He's going to give us an answer. He's going to give us the answer for this question. All right, so his name is, well, it depends on your instructor, obviously. When I was your age, taking an undergraduate physics course as a freshman, his name used to be Kirchhoff. And then over the years, I noticed that, hey, wait a minute, this guy is German. And obviously the pronunciation is not the same as our American pronunciation. And then I tentatively switched to Kirchhoff. And evidently the way they say it's Kirchhoff, they call it Kirchhoff. That's fine. All right, so Kirchhoff, Kirchhoff, same guy, Gustav. This is the guy who was able to solve this problem. Evidently he's also Prussian, German. He came up with an interesting way of solving these problems. So this is one of those rules. These are known as Kirchoff's or Kirchhoff's rules, whatever. All right, so I'll probably keep changing the way I pronounce his name from time to time. It's not intentional, but that's how it is. All right. So this is one of those things that you will get to learn and study when you guys are taking circuits next time. And they're also going to provide you with a little more sophisticated rules, but this is the one that we will get to use at this level. So we got the Kirchoff's rules. The first one is the loop rule, all right, or the voltage rule. They both mean the same thing. And I'm just going to mumble a couple of things, and then I'm going to explain it. Okay, so we've got to start from somewhere. We've got to start where we start. The first couple of things I will say will make absolutely no sense to you, but I'm going to say it so that I can go back and explain it again. All right, so it's called the loop rule. Imagine that you're looping in this direction, and the current is in the same direction. So I'm looping in the direction of the current, whatever that means. All right, so just bear with me. All right, if the current and the loop, if they're in the same direction, there's going to be a voltage drop across the resistor. Okay, good timing. All right, so if the loop, whatever that is, and the current, if they're in the same direction, there's going to be a voltage drop across the resistor. If the current is moving in the opposite direction of the loop, there's going to be a voltage gain across the resistor. All right. If the loop is pointing from a positive terminal towards the negative terminal across the terminals of a battery, there's going to be a voltage drop. If the loop is pointing, in this case, the loop is pointing from the negative terminal towards the positive terminal, there's going to be a voltage gain. All right, so just focus on these 4 rules one more time, and then I'm going to explain it, and then it's going to make sense at that point. Right now, if it's not making sense, it's not making sense because it's too weird, too abstract. All right, so loop and current in the same direction across the resistor, voltage drop. Loop is moving this way, the current is in the opposite direction. All right, this is also known as the Kirchoff voltage rule. All right, so the loop and the current in the same direction, voltage drop. All right, loop is in this direction, current is in the opposite direction, voltage gain. Loop is pointing from positive terminal towards the negative terminal of a battery, which means that there's obviously you're going from positive to negative, so there's going to be a voltage drop. That's what it means. If the loop is pointing from negative terminal towards the positive terminal, obviously you go from negative to positive, so there's going to be a voltage gain. All right, so these are the rules that we will get to play with. There are more rules, but we will focus on them later. Okay, so one step at a time. Okay, so whatever it is that we discussed, let's capitalize on what little we know at this point. Okay, so I'm changing the circuit right now. Set it up as something a little bit more simple, so that we can apply the theory to this circuit. What do we have in the circuit? We got 2 resistors, this one and that one. We also got 2 batteries. Notice that the batteries are not hooked up the same way. All right, this is positive, this is negative, this is negative, this is positive. Okay, so one of the things that we will decide is which direction do you want the current to go? All right, so don't look at the batteries. Pick a starting point. At this point, our starting point is going to be A. All right, I can make the current go this way, or I can make the current go that way. Okay, I can make it go in the clockwise direction, or I can make it go in the counterclockwise direction. It's arbitrary. All right, it's the direction that you pick is a personal choice, and you're free to pick a direction that you like. Math is going to make the necessary corrections. So don't worry about, hey, this is the positive terminal, this is the negative terminal. So don't say it's negative charges are the current, they're going to travel this way. And all of a sudden you go, wait a minute, this is also a negative terminal. So all of a sudden the confusion is going to set in. If you try to solve it conceptually, the way I force you guys to do it, it's not going to work in this case. It's going to cause a confusion. And that's the reason why the Kirchoff's rules is important. All right, so arbitrarily, I want the current to be in the clockwise direction. My personal choice, that's the way we will go. All right. So I decide that the current is going to go this way. You can see the arrows. All right, so it's my personal choice. I say the current is going to flow in this direction. I'm also going to loop in this direction. Is this what happens? My current is going to go in this direction. I'm also going to loop in this direction. The meaning of the loop is I'm going to carry out my computations in the clockwise direction. That's what it means. When I say I'm looping in the clockwise direction, which means that I'm going to start at this point and I'm just going to carry out my computations. I'm going to look at my voltage gains and voltage drops across the circuit in the clockwise direction. That's what it means. So this is the loop rule or Kirchoff's voltage rule. So what we're going to do is we're going to do a little bit of accounting. We'll check to see how much of a voltage drop and voltage gain that we will get from each and every single element of the circuit. All right, so this is the direction we're going to end up looping. All right, so now we're hitting the first resistor. Loop is going to be in this direction. The current is in the same direction. If the loop and the current, if they're in the same direction, what happens? You end up getting a voltage drop across that, right? So if they're in the same direction, but to the loop. All right, so if the current and the loop, if they're in the same direction, you end up getting a voltage drop. If they're in opposite directions, you end up getting a voltage gain. All right, so if they're in the same direction, what's going to happen? We end up getting a voltage drop. All right, so across the first resistor, we're going to end up getting a voltage drop. There has to be a negative here. Okay, finally, I caught up. All right, and here, notice that the loop is pointing from positive terminal to the negative terminal. So there's going to be a voltage drop again across the battery. And then we are right here. Again, the loop and the current, they're in the same direction. So if they're in the same direction, what happens? There's going to be a voltage drop across this one. And then now we hit this battery. So what's happening here is it's jumping from negative terminal towards positive terminal. We're going from negative to positive. So there's going to be a voltage gain across that one. Okay, so that's how you apply it. So now that we mentioned it, so let's write out our findings at this point. So I don't like using numbers. Most physicists don't. We don't really care for numbers because it's much more efficient to express ideas using symbols. So the first resistance, I'm going to call it R1. This is the voltage across the first battery. Instead of using V, we're using epsilon. That's a traditional symbol. Epsilon means electromotive force. Okay, I don't recall if we discussed this yet, but we will in the future. When physicists came up with these concepts, obviously they came up with the concept of electricity. They thought that was an electrical fluid. Okay, it would go from a state of surplus to a deficiency. And they thought that the force which was pushing these charges from a positive state towards the negative state, they didn't know what that was, so they called that the electromotive force. Of course, later the concept of energy was invented, and out of energy we have the concept of voltage. So the voltage and electromotive force, they mean the same thing. So when you see the symbol epsilon, that means voltage. That's the reason why it's got the units of voltage. All right, so this is the voltage from the first battery, the second resistor, resistance of the second resistor, and this is the voltage from the second battery that we got. All right, so there's going to be a voltage drop across the first battery. There's going to be a voltage drop across the first resistor, voltage drop across the first battery. There's going to be a voltage drop across the second resistor, and there's going to be a voltage gain across the second battery, right? So let's just sum them up. All right, so at my starting point, I'm going to loop in this direction. All right, so here's the voltage drop across the first resistor. We're jumping from positive to negative, so there's going to be a voltage drop across the battery, the first battery, and looping the current in the same direction. So there's going to be a voltage drop across the second resistor. And now we're going from negative terminal towards positive terminal, so there's going to be a voltage gain across the second battery. That's it. All right, so the question is determine the current in the circuit. So we got only one single unknown. Obviously, the voltage values are known, so you can carry them across. So it's going to be epsilon 1 minus epsilon 2. The current is going to be common to both resistors, so you can factor that out. All right, so this is voltage drops and the gains conservation of energy. So that's the Kirchoff's voltage rule. That's sum for I, so you guys know how to do it. And then plug the numbers in, which I'm not going to, because I get nothing out of it. All right, so let's get back to problem number 6. All right, so this is the car's electrical system. It's the same as this problem that we started the lecture with. All right, so headlights, that's the resistance of the headlights. The battery, 12 volts. Resistance of the wire connected to the battery, it's going to be very small. Alternator, and this is the amount of resistance that the wires will offer, so it's going to be very small. So what is the amount of current coming out of the alternator or going into the alternator, depending upon how you want to look at it? What is the current supplied by the battery? And what's the amount of current going through the headlights? All right, so what do we have? We got 3 unknowns, which means that we need to come up with at least 3 equations. All right, so this is problem number 6, and this is a problem that you have to kind of practice. All right, so we need to come up with 3 equations. So the question is, how do we come up with 3 equations? The answer to that question is by using the loop rule or voltage rule. All right, so we need to know the amount of current going through the headlights, amount of current coming out of the battery, and amount of current either going in or coming out of the alternator. All right, so we end up using the Kirchoff's voltage rule or the loop rule, meaning that the amount of voltage supplied and the amount of voltage drop across each and every single resistor will add up to 0. So the total change of voltage of a circuit is going to be 0. At this point, I'm also going to introduce the junction rule, something that we discussed before briefly. So the amount of current going into a junction, the total amount of current going into a junction and coming out of it will add up to 0. All right, so at the junction, changing current is going to be 0. If it's going into the junction, it's going to be positive. So I1 is going into the junction, so that's positive. I2 is going into the junction, so it's also going to be positive. I3 is coming out of the junction, so it's going to be negative. So notice that everything adds up to 0. So this comes out of the conservation of charge. All right, so the junction rule is otherwise known as the Kirchoff's current rule. It's the same thing. All right, so this one is the voltage rule. This one is the current rule. Kirchoff's current rule. So when you guys take circuits, they will call it the KCR. This is going to be KVR. They mean the same thing. All right, so how do we generate 3 equations? We need to generate at least 3 equations to solve for 3 unknowns. You can generate 4, you can generate 5. you cannot generate less than 3. If you have less than 3, you won't be able to solve this problem. All right, so my starting point is gonna be B, so we will start at B. And then once again, I'm gonna traverse the circuit, loop the circuit in the clockwise direction. And then I'm gonna sum up the total voltage gain and total voltage drop. Voltage drops as well as the voltage gains will have to sum up to 0. So that's what I'm gonna do. All right, so the first thing that I'm gonna do, I'm gonna take a look at the junction B and then do the Kirchoff's current rule. So I'm just gonna sum up all the currents. So this current is going into the junction, so it's gonna be positive. This current is going into the junction, it's also gonna be positive. This current is leaving the junction, this one is gonna be negative, and they will all add up to 0. Okay, one of the things that I need to mention at this point, I know you're listening, and I know also you guys are following this. Okay, but there's a slight problem here. One of the things that you will notice when you're working on this problem is, how do I know that the current is going this way? How do I know that the current is going that way? And how do I know that the current is going that way? I don't. To answer that question, I have no idea which direction the currents are going. To be honest with you. Okay, these directions are assigned arbitrarily. Okay, meaning that, hey, I feel like the current may be moving in the opposite direction. I don't know which direction it's moving. Okay, you arbitrarily assign directions to current. And at the end, I will show you how to make the corrections, because mathematics is going to tell you. All right, so I'm just, this is the junction rule, so I'm just summing up all the currents. So this is going into the junction positive, this is going into the junction that's positive. This one is leaving the junction, so that's going to be negative, right? They sum up to 0. Okay, so I came up with 1 equation, so this was awesome. I'm feeling good. Now I need to come up with 2 more equations. All right, now this Kirchoff's rules is crazy easy in terms of generating equations, the number of equations that you want to generate. So as long as you can literally take the circuit and break it into components that you're interested in. Okay, so the next thing I'm going to do is I'm going to just focus on this portion of the circuit, and I'm going to apply my Kirchoff's rules to this portion of the circuit, okay, to come up with 1 more equation. So I'm going to loop in this direction, all right, and then also the current is moving in the same direction. So current and the loop, they're in the same direction. So there's going to be a voltage drop here. We will come down here, and notice that the loop is pointing from the negative terminal towards the positive terminal. So there's going to be a voltage gain here. The current and the loop in the same direction. So there's going to be a voltage drop here. Okay, so I can literally break the circuit into components and apply my loop rule to that portion. So this is the portion of the circuit that I'm going to be focusing on. Voltage drop, voltage gain, voltage drop, and that's it. They will add up to 0. So this is my first resistance, this is my first battery, and this is my second resistance. So headlights and battery, R sub H, R sub B. All right, so there's going to be a voltage drop. So this is the current that's going to be going through the headlights. All right, so the current going through the headlights, and this is the resistance of the headlights. So we got the voltage drop right there. We'll come back down, hit this junction, and go left at that point. Across the battery, this is our battery, so there's going to be a voltage gain. So we're going this way. All right, so this is our voltage gain. Okay, so now this is the current coming out of the battery. So notice, don't get them confused. This is I sub H, this is I sub B. All right, so current and the loop, they're in the same direction. So which means that there's going to be a voltage drop across this one. Okay, cool, I captured that. All right, and that's it. We got to the same point. So the voltage drops. Okay, we got voltage drops across the resistance and voltage gain by the battery. They will add up to 0. That's our second equation. All right, so now we need 1 more equation. All right, and once again, using the Kirchoff's rules, it's easy. So now let's just loop around the lower section of the circuit. We could do the same thing. Let's start at B, go this way, come back down, go this way, and go back at the same point. And then just sum up all the voltage values, drops as well as the gains, and equate them to 0. So that's what we will do. All right, so that's our next step. Okay, so I'm going to once again loop in this direction. Okay, notice that this time I'm going to be going in the opposite direction of the current. So across this resistor, there's going to be a voltage gain. And I'm looping in this direction. This time I'm going from positive terminal towards the negative terminal. So there's going to be a voltage drop across this battery. And then I hit the junction going the downward direction. I hit this voltage supply, in this case, alternator. I'm going from negative terminal to the positive terminal. So there's going to be a voltage gain, current and the loop there in the same direction. And there's going to be a voltage drop. So voltage gain, voltage drop, voltage gain, voltage drop, and then they will add up to 0. All right, so that's what I expect to see. All right, so let's focus on this one. The current of the battery loop is in the opposite direction across the first resistor, across the resistor of the battery. So there's going to be a voltage gain here. There's going to be a voltage drop here across the battery. There's going to be a voltage drop, voltage gain across the alternator. It's going to be epsilon 2. Okay, and then current and the loop are in the same direction. So there's going to be a voltage drop across the second resistor. Okay, and then that's going to add up to 0. Cool. Now we got 3 equations and 3 unknowns. Okay, technically speaking, this is as far as physics goes. All right, you can use substitution method. I don't recommend it. That would take forever. That sort of stuff gets real complicated and easy to make mistakes under the circumstances. You will have to use your calculator. Obviously, when you guys have taken higher level courses, make sure that you have a calculator that can handle these kind of things. If you know how to use linear algebra, I would recommend that you use linear algebra. You can set things up using matrices. Obviously, this is very easy to calculate. MATLAB is kind of standard for engineering students. If you don't know how to use it, I would recommend that you learn how to use it, because these kind of problems, this is not sort of stuff that you want to do by hand per se. All right. If I ask you a question like that, obviously I would expect you to be able to use MATLAB or your calculator. All right. But 95% of your credit will come from just being able to set up these equations. All right. So I'm not going to finish up the work. I'm not going to do it mathematically, obviously, but there are a couple of things that I'm going to show you at this point. All right, technically speaking, there's one more equation that we can generate. Okay, so I'm just going to show you the next step. And then, all right, so by using the outer portion of the circuit, you can come up with one more equation. All right, so why don't we just loop around using the outer portion, skip the middle section, and then use the outer perimeter of the circuit, and then come up with one more equation, doing it that way. All right, so once again, we will get started at point B. I'm going to traverse the circuit in this direction. All right, so one of the things that you will notice is now the loop and the current there in the same direction. So there's going to be a voltage drop here. We will hit point D and then hit E and then go down to F. And then there's going to be a voltage gain. There's going to be a voltage drop, and that's it. All right, voltage drop, voltage gain, voltage drop, and that's going to become our 4th equation. All right, so that's going to represent, this is the resistance of the alternator. All right, so there's going to be a voltage drop across the headlights. There's going to be a voltage gain across the alternator, and there's going to be a voltage drop across the wire of the alternator, and everything's going to add up to 0. All right, so we came up with 4 equations, and we got 3 unknowns. We got plenty of equations to solve this problem. Okay, I'm not entirely sure if these numbers are correct, because this is happening during a lecture over the summer. I will leave it up to students to do the numbers. I'm not sure if these numbers are correct. More than likely, I made up these numbers because I want to make a point here. Okay, so go with me. I don't think these numbers are correct. Okay, just take my word for it. The reason why I came up with these numbers is because I want to make a point here. The point is this. This is the amount of current coming out of the alternator. This is the amount of current going through the headlights. And this is the amount of current supplied by the battery. Okay, so I hypothetically came up with 3 numbers. What's important here is the signs in front of these numbers that I need to focus on. Okay, so what that means is, if you see a positive number after you're done with the computation, the direction that you arbitrarily assigned is correct. I assume that the current was coming out of the alternator, and I've done the calculations, and all of a sudden I end up getting a current value which is positive, which means that my arbitrary direction happens to be correct. Alternator is literally supplying the current. Obviously, it's just charging up the battery. So this was correct. I assume that the current was going through the headlights in this direction, so that's also correct. But this assumption that the current is coming out of the battery in this direction is not correct. And how do I know that? Because I end up getting a negative sign, which means that the actual direction of the current is in the opposite direction. So the current is actually going this way. All right, so the current is actually going that way. That's the meaning of it. All right, so when you come up with numbers like that, if your arbitrary direction that you pick, and you don't need to really think about it, because just thinking about it is going to cause a lot of confusion, because you got a battery and you got an alternator, and notice that they're polarized the same way and they're kind of attached to each other kind of the same way in essence. And all of a sudden, if you're thinking too much about it, it's just going to cause confusion. Alternator in this case is just charging up the battery, obviously, and then it's also adding on to the current, which is going to be going through the headlights. All right, so.
And while these elements can be combined into networks of ever-increasing complexity, they always obey the same simple rules, called Kirchoff's laws. Gustav Kirchhoff, a German physicist, was keen on mathematics. By applying Ohm's law and generalizing it fully, he derived 2 laws, and each expresses a familiar idea. One of those ideas is conservation of charge. And the corresponding law for circuits is, whenever one current splits into 2, or vice versa, the total current into the junction will equal the total current out of it. Kirchoff's other law expresses conservation of energy. An electric charge going around any complete circuit neither gains nor loses energy. Consider an electric charge in space, not confined to a circuit. If it's moved through space on a path that brings it back to its starting point, no net work is done. The electric potential, or voltage, may go up or down, but it always gets back to where it started, and the same is true inside a circuit. Notice that an integral along a closed path has a special notation, an integral sign with a circle in it. So, in the special case of an electric circuit, all the voltage rises due to batteries and charged capacitors, and all the voltage drops due to currents flowing through resistors add up to zero. Using these two laws alone, engineers analyze the most complex circuits.
All right, that's it. You guys are genius. Or was I genius? More like that. Anyway, so how do we control the discharge time? 2,000th of a second, guys. That's it. 2,000th of a second. 20 amps of current. Right into the chest cavity. That's it. Controlled lightning. How do we get to control the amount of charge? The amount of charge that we're going to administer. That's 20 amps of current. 20 amps of charge. 20 amps of current. Within 2,000th of a second. How do we control the discharge time? So that, likewise, this is what is it? 0.3 of a millionth of a second. How do we get to control that? So we are dealing with capacitor. All right, you control the delivery time or the discharge time using resistors. All right, these are known as RC circuits. Resistor capacitor circuits, in essence. All right, you can charge it up, so you got the switch, just throw it up. All right, so the battery is just going to charge up the capacitor. Obviously, if you have a resistor, what's going to happen is it's just going to delay the charging period. All right, so by using a resistor, you can control the charging time, in essence. All right, so which means that you can charge it up slowly or you can charge it up fast. Okay, so this is just going to charge up. Or you can discharge it. And how do you do that? Obviously, throw the switch off. And whatever the charge here is, it can decay. So now it's going to discharge. Okay, discharge happens exponentially. So there's an exponential decay. And then you have a gradual charging time. This thing is not exponential, but this thing is. Okay, there are two equations. You guys can know. All right, so this is problem number 7. Problem number 7. Okay, so let's not worry about it. We'll get back to problem number 7 shortly. So what is it that determine the value of the resistance? We just want to charge this up. Capacitor recharges within a time constant of 3 seconds. So whatever that is, we have to discuss that. And okay, whatever. There's something else that I want to emphasize. Let's get back to the Kirchoff's rules. There's more. The more is right at the bottom. So that's what I want to focus on. Okay, so what happens across a capacitor is what I'm interested in right now. So let's focus on that one. Notice that the current is charging up the capacitor in this direction, and the loop is also in the same direction. So if the current is charging up the capacitor in the direction of the loop, we end up getting a voltage drop across the capacitor. So that's the notation we will use. All right, so net charge per capacitance is related to voltage. So this is going to represent a voltage drop across the capacitor. If current in the loop, if they're in opposite directions, there's going to be a voltage gain. All right, so voltage drop, voltage gain. Voltage drop, if they're in the same direction, if they're in opposite directions, there's going to be a voltage gain. All right, the only thing I'm interested in is actually the derivation of this, and then the meaning of the formulas. The problem solving at this level is fairly straightforward. The problems are not that complicated. Just want to make sure that you guys understand the concept. All right, so I'm going to throw the switch on. The battery is going to charge up the capacitor, and the resistance is just going to delay the process. So this thing is going to charge up gradually. That's what's going to happen. All right, so we end up using the Kirchoff's loop rule or the voltage rule. So what's going to happen is, I'm going to loop in this direction. And then the current is going to move in this direction. It's just going to charge up the capacitor, right? So the current and the loop in the same direction, so there's going to be a voltage drop. The current and the loop in the same direction, there's going to be a voltage drop across the capacitor. And then now we get to this point and notice that the loop is pointing from a negative terminal towards a positive terminal, so there's going to be a voltage gain. So this is the sum of all variations of the voltages within the loop is going to add up to 0. Sum of all voltages, gains, losses will add up to 0. So that's the conservation of energy. All right, so boom, boom, boom. All right, so I'm looping in that direction. So there's going to be a voltage drop there, which is this. There's going to be a voltage drop across the capacitor, which is this. And then there's going to be a voltage gain here because you go from negative terminal to the positive terminal. So that's going to be this term that we got. Okay, so we got that. All right, so what do we do with that? Boom. Obviously, you can follow the algebra. So move this across. This becomes negative. Everything is negative on the left-hand side as well as the right-hand side. Negatives, just multiply both sides by negative, so this becomes positive. And then let me check to see how far I want to take this with you guys. I'm just going to take it for as long as it goes because there's a little bit of calculus here. As soon as we get to differential equations, I will stop because it's not a prerequisite for this course. All right, so here's the current value, and then you got the net charge. The current is net charge per second. The current represents how fast the charges are moving in the same direction, how fast the charge is changing per unit of time. So this is an expression of current dq dt. This represents how much the net charge is changing within a certain time period. And all of a sudden, this equation can be represented in terms of changing charge here. All right, and then obviously divide both sides by r, and then you come up with this expression. And this is as far as we will go. The next step is going to be, the next step is known as differential equations. All right, so this becomes a first order differential equation, which is now a requisite for this course. And then that's the reason why I end up doing a fast forward. Finish out the differential equation. It's going to look like that. Okay, so this is the formula that we need to discuss, the meaning of this formula. Okay, so this formula represents this graph. Okay, so obviously what you're looking at, this is the net charge. What this graph and what this formula says, it says, hey, listen, our capacitor is just going to charge up. This formula represents how fast the capacitor is going to charge up within this time period. And so that's the meaning of the formula. So the visual representation, graphical representation of this formula is right here. All right, so it's going to charge up to this value. Q naught represents the maximum value that you can charge it up to. Just remember, Q naught is the maximum value that it can charge up to. So you got your 1 minus, you got E raised to the power of negative T divided by RC that you're looking at. So I'm just talking about the obvious, but let's just focus on the less obvious stuff. Okay, the stuff that is going to be important in the future. All right. When you're looking at an exponent of anything, all right, you know that time is going to have the units of seconds, and the time variable is divided by RC. So you got the resistance and capacitance values, right? So when you multiply resistance and capacitance, so the question is, what will be the units of this combination? Okay, for those of you guys who are ambitious enough to go to grad school, at some point you will have to take a GRE test. A lot of the colleges, universities require that. And this is a typical GRE test question. Okay, this requires a little bit of understanding of mathematical reality. How much do you really grasp the reality of mathematics? Guys, exponents, just remember this for as long as you can before the Alzheimer's kicks in. All right, the exponents will always be unitless. If you're looking at the exponents or the powers of anything, they will be unitless, which means that time is the units of seconds. And RC, combination of resistance and capacitance, will also have the same unit, which is going to be seconds. Time is going to be in terms of seconds. RC is going to be in terms of seconds. This is the reason why the product of resistance and capacitance is usually known as the capacitive time constant. So it's going to be expressed in terms of seconds. All right. All right. So we end up using capital tau. It's a Greek letter, otherwise known as capacitive time constants. So the question is, what does it represent? Well, it represents the amount of time it takes for a capacitor to charge up 63% of its maximum. That's what it means. All right. So it represents the amount of time it takes for the capacitor to charge up to 63% of its maximum. That's what it means. Technically, that's what it means. All right. So that's the book definition, which I'm not going to be too interested in. It's that it tells you how fast the capacitor is going to charge up or discharge. Okay. Let's use commonsensical definitions. Stuff that's going to stay with this. Stuff that's going to stick. All right. All right, so what's important here is the capacitive time constant is important because it's going to tell you how fast it's going to charge up or how fast it's going to discharge. All right, so think of it this way. Larger the resistance is, longer it's going to take, guys. Larger the capacitance is, longer it's going to take. Both of them make sense. Resistance is going to slow down the charges. Capacitance tells you how much charge you can store in something. It's the ability to store charge. I kind of play with the definitions. It's the amount of charge that you can store. All right, more charge that you can store in something, the longer it's going to take. Are you running this? The longer it's going to take, the larger the resistance is, the longer it's going to take. A lot of it is, once again, intuitive at this point. All right. So you see this formula, it's just this formula, when you use it, whenever you're charging up a capacitor, you can control the charge up time by controlling the amount of resistance. You can control the charge up time by controlling the amount of capacitance. Smaller resistance means you're going to be able to charge it up really fast. Smaller capacitance means you're going to be able to charge it up real fast. So that's what it means. All right. Another thing that I'm going to emphasize. All right, so this is the maximum value that it can charge up to. And RC is the capacitive time constant. It's going to tell you how fast you can charge it up. Okay? Ignore the book definition. It's a nerdy way of saying, well, that's the amount of time it takes for you to be able to charge it up to 63% of its maximum. I just go to hell. Just, it's how fast you can charge something up or discharge it. The other thing that I'm going to emphasize is, okay, let me check this out. Okay, so I think I emphasized the hell out of this one already. All right, discharge. All right, so now we're discharging our capacitor. Again, we're using the Kirchoff's loop rule. And then once again, the current could be expressed in terms of how fast the charge is changing within a certain time period. And then you can turn this into a differential equation, first order differential equation, or at this point, you can actually solve it using calculus. And then when you solve it, this is the equation that you will come up with. Okay, so I'm just skipping through the derivation at this point. Let's focus on the meaning of the formula. You have a pretty good idea right now. The meaning of now, it's going to be a discharge. It's an exponential decay that we're looking at. RC is once again the capacitive time constant. This time, the capacitive time constant is going to represent how fast it's going to discharge. All right. So once again, the larger the current, larger the resistance is, the longer it's going to take. Larger the capacitance is, the longer it's going to take. Now you can control the discharge time. Small resistance, small capacitance, boom, you're done with it. It's that fast. So it's going to go from this maximum value to 0 within a flash. All right. So that's how it is done. All right. So now we're going to deal with a little bit of algebra. Okay. I hate to do it at this level because you guys are taking calculus physics. And I'm usually surprised that I have to actually go over some basic algebra because despite the fact that most of you guys are taking calculus and differential equations, sometimes people get stuck on simple stuff. All right. And this is one of those things, surprisingly. So let's do a simple algebra stuff. All right. So this capacitor charging up. All right. So there are two equations available, both equations the same. You're charging this up to this maximum value, or you're charging up the capacitor to its maximum voltage. I don't care which one you're looking at. All right, so either equation, what is the resistance of the resistor within the circuit? All right, let's just isolate that. So this is a good review in case there's a test question that requires this kind of algebra. So isolate resistance. All right, so what I'm going to do is I'm going to get this term, exponential term, all by itself first. All right, so divide both sides by the maximum charge value. And then obviously I move this that way, and then this goes across the other side. And all right, so this, hold on, this became positive. Very good. This became negative. Okay, I'm good right now. All right, so this is, what's the next step? And most of you guys usually go, oh, I'm just going to take the natural log of both sides. Okay, that's fine. You can make it work any way you want at that point. But I do have my own way of doing it. Preferences through experience. I don't like negative exponents, so I'm just going to get rid of this negative. The way I will do it is I'm going to invert both sides. All right, that's what I'm going to do because I don't like negative powers usually. All right, it makes it complicated, and sometimes you lose your negatives, and then numbers don't make sense. So I end up inverting both sides. That's the meaning of it. All right, so negative times negative is going to be positive, and all of a sudden this, when this becomes inverted, it's going to look like that. This is going to be indeed, this becomes the denominator term on the right hand side. Now I'll take the natural log of both sides. All right, e and natural log will be inverse functions, so it frees up the time term that I'm looking for, the exponential, the power of the exponential. On the right hand side, what do we have? You got the ln of this divided by that. The denominator is going to appear as the negative of the ln, natural log. All right, so natural log of 1 is going to be 0. You don't need to make it this long or complicated, but this is a good exercise. So this term goes to 0. And then at this point, you can isolate our simple algebra. I usually switch these denominator as well as the right hand side of the equation. Because there's some multiplication, I can swap this with the right-hand side. Or isolate it, and that's it. At that point, you can plug the numbers in, and then you're done. If it's a numeric. Okay, so just wanted to give you that. Okay, so problem number 8. Do I want to do this? Hold on. All right, just want to make sure that we got enough time for everything. All right, let's do this. 6:21. All right. Just want to cover everything because it's simple enough. All right, so what are we dealing with? This is a discharge situation. So this capacitor is already charged up across a resistor. All right, so we know the resistance of the resistor. Now it's allowed to discharge, so it's going to be discharging. So it's going to lose 63.2% of original charge within 8.3 seconds. All right, so the question is, what is the capacitance of this capacitor? All right, let's play with this one. So this is problem number 8 from the handout. Problem number 7 is the one that we were looking at before. So if I don't have the solution for it, then you have to do it. It's more than likely it's in my handout. All right, so this is the one that we're focusing on at this point. So resistance value is given, the time is given, so it's going to charge up to 63% of its. It's not going to charge up. It's going to lose its charge to 63% of its maximum value within this time period. All right, so we end up using the discharge equation for this one. So what is the required capacitance so you can discharge it to that value within 8.3 seconds? All right, so this is the maximum value. So it's going to be losing 63.2% of its maximum charge within this time period. All right, so which means that the leftover charge is going to be the total charge minus the amount of charge that it loses within this time period. Okay. All right, so. All right, so the next step is to solve for C, obviously. All right, so get rid of the maximum charge. All right, I'm going to invert both sides so that the power of my exponent is going to be negative, positive. All right, and take the natural log of both sides to get rid of the exponential term. And then what are we doing? C is what I need, so I'm gonna swap this with R. And that's it. And then you plug the numbers in, and whatever the expression you come up with, okay, is good enough. So the maximum charge is gonna vanish, and then you plug the numbers in, which I won't, because it's happening during a lecture, and then that's it.
Consider
At least you guys know how to do it now.
a capacitor connected to a resistor and a battery. Even as the capacitor charges, the total rise in voltage equals the total fall around the circuit. A capacitor in an electric circuit stores charge, much the same way a reservoir stores water for later use. And it takes time to fill or empty either one. How much time? That depends, of course, on how big the reservoir is and how much resistance there is to the water flowing out. The bigger the reservoir and the more the resistance, the longer it will take. Exactly the same is true of charge draining from a capacitor. And applying Kirchhoff's laws, the time is found to be equal to the capacitance times the resistance.